Hello there everyone and welcome to another TOPIQ webinar. Today we'll be hearing about high pressure crystallography from Laura Vendier from the Laboratory Coordination Chemistry of the CNRS in Toulouse. So before we get started, I'd just like to make some announcements as usual. So firstly, I'd like to point out that we are recording this webinar. The recording will be made available via our usual channel, so that will probably be YouTube. As usual, so check our YouTube channel if you want to catch up with this recording later on. We'll also probably post a link to it on our forum. Throughout the course of this presentation, please feel free to use the Q&A button to ask any questions. We'll collect all of the questions and ask them to Laura at the end of the presentation. I'd also like to invite you all to join our forum, so please check out the link here or use the QR code to access our forum and join if you're not a member already. On there, there's lots of useful information, past presentations and details of our activities at conferences and things. So just to let you know that our next TOPIQ webinar will be at the end of May, so on the 29th of May. And it will be same time as this. 29th of May is a Wednesday. If you'd like to register for that one, please use this QR code here. I'll just leave this up for a second longer for you to try and use it if you would like. And then I will move on to introducing Laura. Okay, so Laura has very kindly agreed to speak today about her experiences with implementing a 120 DAC on the CrystallAB Synergy system. So this should be very interesting to any of you who are interested in trying to do high pressure research on Rigaku instrumentation. So just a little background on Laura. Laura has been a crystallographer for over 25 years, and she I think did a brief stint at Georgia Tech in the US back in the end of the 90s, early 2000s. And she's currently at the LCC CNRS in Toulouse. So Laura, if you're ready, please take it away and I'll see you at the end.
Okay, I try to share my screen. Okay, so good afternoon, everyone. Before presenting you the high pressure studies that we are carrying out on the Rigaku laboratory diffractometer, the XtaLAB Synergy, let me first present the context of my work. I am in charge of a crystal chemistry platform, which is open to a whole community of chemists in Toulouse, in France, and more particularly to my laboratory, the LCC, which is a CNRS unit with 250 researchers, and which is a major player in organometallic chemistry in France. So in the X-ray facilities, we work on many kinds of samples, powder, thin layers, but most particularly, we work on single crystal, which is our main activity. We are 3 engineers working on this platform. We have so far carried out many single crystal XRD studies at very low temperature, but recently we have started to study XRD under high pressure. So the goal of my presentation today is to demonstrate you that it is now possible to carry out studies under high pressure with very good quality results, publishable results, on a home diffractometer. So in our case, this is a Rigaku, the Synergy XtaLAB, even without being basically specialist in high pressure. And thanks in particular to the very good usability of the diffractometer, of the Synergy, and of its associated softwares, CrysAlisPro and CrysAlisRed. Thanks to the implementation of a large opening angle diamond anvil cell, 120 degrees, on this diffractometer, we succeed to determine and refine low symmetry crystal structures. Concerning the history of high pressure studies in our laboratory, everything began in 2010 with the acquisition of a Gemini diffractometer. So from Oxford Diffraction, which is now Rigaku. This diffractometer was equipped with two standard X-ray tube, copper and molybdenum, and with a CCD sapphire detector. We had already a DAC, which was actually with a very small opening angle, only 75 degrees. Thanks to a first collaboration with Oxford Diffraction, we got, with the Gemini, a high-pressure setup. So it was made with an adapted beam stop with short collimator. And already, even in 2010, CrysAlisPro and CrysAlisRed made easier the data collection strategy and the data integration for high-pressure data. For high-pressure studies, it is recommended to use short wavelength, silver or moly, to get good compactness. And so on the Gemini, when we carried out these experiments, we used, of course, the molybdenum tube. At that time, the high-pressure cell and all the X-ray analyses under high pressure were fully supported by Dr. Elena Shepard, who was part of the team Switchable Molecular Materials. Elena is an international expert in high-pressure study and a high crystallographer. Concerning the advantages of this first high-pressure setup, first of all, we have to say that it's easy to install the high-pressure setup, beam stop, short collimator, and also the DAC, which is mounted on a regular standard goniometric head. As I said already, CrysAlisPro and CrysAlisRed are a good help for the strategy and the data processing. The main limit of this first system was the small opening angle of the DAC, which limited us to high symmetry system. So that was not really adapted to our needs because the materials we are investigated are low symmetry, like triclinic and monoclinic. Another problem was that at the time the Gemini was equipped with a standard X-ray tube, not microfocus. So with a wide beam, low intensity. So as a result, this high pressure setup on the Gemini was mainly used to prepare synchrotron experiments, to test some crystals that were after analyzed on the synchrotron. In 2020, we were fortunate enough to be awarded a regional project dedicated to research and innovation platform, which enabled us to acquire a new diffractometer. So we got the Rigaku XtaLAB Synergy-S, equipped with double microfocus tubes, copper and moly, and with the IPX detector. At the beginning, we considered the possibility of choosing a silver anode rather than a molybdenum, because, as I said, for the high pressure experiments, it's better to have short wavelength. But we test first samples of our laboratory at the Rigaku laboratory, and actually in terms of diffracted intensity, the moly was better suited to our samples. So this is why we chose the moly. Thanks to this project, we could also buy a new DAC. So it's a DAC from Almax. This is the Almax EasyLab 120 DAC with an opening angle of 120. We could buy as well a drilling machine for the gaskets of the DAC. And this project was a collaboration with Rigaku. So we have been lucky to have in our department a high pressure expert engineer financed by Rigaku, who is the Dr. Damian Paliwoda. He helped us to choose the DAC and to implement it on the Synergy. And he trained us for the high pressure studies by XRD. So here is a schematic view of the DAC with the diamond here, the backplate, the opening angle. Here you have the gasket. In the middle, you put your crystal with the X-ray coming in and coming out. Oh, sorry. I put this unique cell with a physical angle of 120 degrees on both sides is particularly well suited for single crystal diffraction. So it allows a large access to the reciprocal space whilst carrying out measurements at high pressure. You can see on this nice diagram in green the portion of the reciprocal space available with the small angle DAC we had before, 75 degrees. And in pink, you can see what we have now with the new DAC, a 120 degree opening angle. On these two pictures, you can see our pressure setup, high pressure setup on the Synergy. As I said before, we work with the Molly radiation for the completeness. Here you see well the DAC mounted on the regular goniometer head. You can see also the short collimator, the beam stop, and the cryostream, which is raised to high position in order to avoid any collision and also for not annoying the X-ray beam to come in the cell. I really want to emphasize the advantage of working with a microfocus for the high pressure studies. Not only is the high intensity of interest, but more particularly the fineness of the beam compared to the beam of a standard tube, which allow us to focus on the sample only, and thus help avoiding spurious signals, like the diamond signals, the gasket, and so on. Here is a picture of our drilling machine for the gasket. So the gasket is of single use. It is in stainless steel. The drilling machine provides 0.4 millimeter hold. We bought this drilling machine from the Roman Marciniak company, which is in Poznan, in Poland. I will present you now how we handle and load the DAC. On this picture, the DAC is open. You can see here the location notches to help us to close correctly the DAC once we have loaded. Here we see how we put the gasket on one of the anvil. We do that with the help of a microscope. The gasket should be very well centered on the anvil, as you can see here. Concerning the loading of the crystal into the cell, as you can see on this picture, we have our little crystal. The size of the crystal should be around 200 micron, not too big, of course, but not too small as well, because it's easy to lose your crystal. Loading the cell is quite the trickiest part of this job. It can be very difficult. The crystal is immersed in a Daphne oil in our case. This is a medium for the application of the pressure. The maximum pressure will depend from the medium. In the case of our studies for the moment, the maximum pressure we want to reach is few gigapascal, and so the Daphne oil is a good medium for that. Then we put a small ruby in the center of the upper anvil, and the ruby is used as a pressure indicator that we will check by Raman spectroscopy. To gradually apply pressure, it is recommended to tighten the fourth screw by approximately 5 degrees, starting by the opposite screw, 1, 2, 3, 4. As I mentioned before, we use the ruby fluorescence to determine the applied pressure. Before applying any pressure, we first determine the fluorescence of our reference ruby at ambient pressure. So now we are going to have a look of how we can center the crystal on the diffractometer. But before doing anything, it is important, when you will launch CrysAlisPro, to choose the high pressure setup and to have previously mounted on the diffractometer the correct beam stop and the short collimators. A good thing for us is that CrysAlisPro will always ask you what configuration is on the machine, on the diffractometer, in order to avoid any collision. We will now have a look to how we can center the crystals on the Synergy. So in the first step, we will check the horizontality with a spirit level, as you can see here, and we can adjust it manually if necessary. Then we can start the center of the crystal and focus of the camera by switching the position of the cell between 0 and 180 position, between the two positions, several times to achieve the best centering and focusing, as you can see here. The next step is to carry out a pre-experiment to determine the compound cell and to, above all, fine-tune the crystal centering by checking the wobbling angles. In CrysAlisPro, we will choose the high-pressure setup option as shown here by clicking first by Start New, then Over Experiment, then High-Pressure Pre-Experiment. And at that point, we will indicate the DAC opening angle. Then it's possible to run the pre-experiment and to perform the cell determination. Once the cell is determined, we have to refine it. And when we'll have refined it, we will be able to check the wobbling angle. So the X parameter is the most important. Its value must be not greater than a third of the thickness of the crystals. If it is not the case, it's necessary to redo the crystal centering, then to redo the pre-experiment with the cell determination, refinement of the cell, and checking of the wobbling angle, the X parameter. Once you are happy with that, then it's possible to run the strategy on CrysAlisPro in a quite regular way, as you will do for regular experiments. Once the data collection is finished, it is recommended to do regular peak search, cell determination, and to check your reciprocal space. It is possible to remove the diamond peaks, the spurious peaks, in the images directly. But in our opinion, it is easier to deal with those spurious peaks once you are refining your structure. For example, when you are using Shell XL, by checking the most disagreeable reflection and by removing the worst with the omit command. When performing the data reduction in CrysAlis using DC Profit, we specify that the analysis was carried out in HP configuration. And so we can indicate here the opening angle of the deck, and it is recommended to reject the reflection with bad profile. For the data finalization, the scaling, empirical absorption, and detector sensitivity correction are performed by using the DC RRP command in CrysAlisPro. It's good to know that it's possible to perform HP cell absorption correction by using an external program, which is called Absorb, and which is developed by Ross Angel. This program requires two files. First of all, the input file containing the reflection data generated automatically during the data reduction, and also an experimental file that contains all the information about the crystals, the diffractometer, and the diamond cell geometry. For more detail, I encourage you to go to the website of Ross Angel. So, The XtaLAB studies pressure is a powerful technique to better understand the structural property relationship of materials. If we consider pressure as an external stimulus, it is a thermodynamic parameter that significantly influences material properties. But its effects on chemical reaction, materials property, electronic structure, are relatively poorly understood until now, probably because of a lack of experimental data. This lack of high pressure information, compared to the large amount of low and high pressure temperature data, is due to the high pressure technical requirements. It is true that the DAC design made possible the development of high pressure as powerful tool for spectroscopic and X-ray diffraction studies, allowing material to be compressed at pressure up to several hundred gigapascal. In our case, thanks to our new type of DAC with a large opening angle, 120 degrees, we were able to determine crystal structure of low symmetry, like triclinic and monoclinic systems, which is quite rare for laboratory experiments. So here is an example of XtaLAB study of a single crystal under high pressure and low temperature that we carried out on a molecular iron 2 complex. Thanks to this study, we were able to highlight a coupling mechanism between the spin transition and a structural transition, accompanied by a break of symmetry in the molecular complex. It was shown that the coupling between the two phenomena can be controlled by the external stimulus. Particularly under pressure, the spin transition can be separated from the structural transition, which is not possible to detect at low temperature. So here you have the low spin state before applying the pressure, which is a monoclinic C2/C. And when applying the pressure, we have this breaking of symmetry and we have a triclinic P-1. So this study clearly highlights the preponderant role of the application of pressure to better understand the structural property relationship of a material. In our case, without this high pressure study, we would never have highlighted the fact that the spin transition can be separated from the structural transition phenomena for this molecular iron complex. Before concluded, here are the CheckSIF, the two CheckSIF of two structures. One is monoclinic, the other one is the triclinic one. So the data of this structure were recorded under high pressure on the Synergy laboratory diffractometer. We can see the good quality of the data, very few alerts, only C-type alerts, and no concern for completeness, although the systems are low symmetry. So we can say, to conclude, that the opening angle of the DAC, 120 degrees, associated with the fineness of the X-ray beam produced by a microfocus tube, the very good quality of the detector, the HiPix detector, help a lot to get such good results. So in conclusion, I would like to thank a lot of people. First of all, the two XRD high pressure experts we had the luck to work with, Dr. Elena Shepard, who is now at the University of Kent, and most particularly Damian Palioda, who now works at the new European Spallation Source and who helps us really a lot to begin those high pressure studies. In my laboratory, I would like to thank my colleague, Mrs. Doyon and Malela Deha, who work with me at the X-rays facility. My colleague from the Raman facility, Madame Tassé, and also all the team, the switchable molecular materials team, most particularly Azedine Bouseksou and Gabor Molnar. Concerning the financial support, we want to thank the European Research Council, the Région Occitanie, and of course, Rigaku for the collaboration, the grateful collaboration. And I thank you for your attention today. Please do not hesitate if you have any question.
Thank you very much. That was a lovely presentation. So we have had a few questions come in while you've been talking, and if anyone else would like to ask a question, please feel free to add them to the list and we'll handle them as they come in. Okay, so the first question is it possible to run powder in the diamond anvil cell as well using the same setup?
In our case, no. We tried and the results were not very good, actually. I think we did not, but it would be more recommended to adapt that kind of high pressure cell on a powder diffractometer, like a smart lab. But I'm not an expert, so I don't want to say bad things. What I know is here in our laboratory, when we want to do high pressure on powder, we go to synchrotron. This is what I can say.
Okay, I'll just, if I can just add to that, that we do have some customers who have done this. I have not personally done it either, so I don't know how easy or how successful they've been, but I do know that there are people attempting to do it. Okay, so how do you ensure that the diamond anvil cell holds firmly in the goniometer head without slipping, just by tightening the head screws?
Yes, exactly. Yes. So of course we have to be careful with that. We have really to tighten very strongly in order to have the DAC moving during the experiments. But it's okay. It's fine. Mm-hmm.
Yeah, I'll just add, I would say that not all goniometer heads are made equally, and some manufacturers produce better goniometer heads than others that hold the cells better. I would point you towards the Huber heads.
Yes, exactly. We have Huber heads in our laboratory. I confirm.
Okay, isn't there an optical distortion due to the diamond during the visual centering of the crystal?
Actually, we have a distortion because the crystal is in the cavity of the gasket. And so this is why we have to adjust the focusing of the camera. So as I said, we are turning between 0° and 180 degrees for the position of the cell. And we are doing that step by step. So we touch a little bit the centering of the cell and then the focusing of the camera until we have on the screen a nice image. Okay. And the wobbling, the checking of the wobbling angle is really the important part, actually. So it's a little bit time consuming because you have to first do a rough centering by optics, by checking with the camera, but then you have to do the pre-experiment, determine the cell, refine the cell, and check the wobbling angle. And if the wobbling angle is not good, especially the X parameter, then you have to retouch again the centering of the crystal, of the cell, actually, of the DAC.
Okay, maybe if I may, I'll just add to that this is less of an issue these days because a lot of the diamond anvil cells you buy now are better constructed, but some diamond anvil cells, the diamond can become misaligned, and the optical effect of the diamond can make the center of the crystal appear to be in a different place. Then you have to kind of come to a, let's say, halfway house between the two image positions when you flip the cell over. So you go one step together.
Exact.
And that can be tough. So yeah, it's mounting the cells on the system is a skill, and people who can do it are the people you can go to ask for help with that.
I would add that to get such high opening angle help as well, I guess, a little bit. Because there is some room for the crystal. It's not too tightened and you can really focus on your crystal.
Yeah. Okay, next question is, how do you measure at low temperature and high pressure Do you have?
So no, we did not. It's big. I think yeah, I understand your question, and maybe I was not clear. Actually, that was two different experiments. First of all, we study our crystal at low temperature, as you probably do all on your diffractometers using the cryostream, and then we remove the cryostream, we load the crystal in the DAC, and then we mount the DAC and we do the high pressure experiments. So it's two different experiments. With this cell, we don't have the possibility to combine both. But I know that Almax buy a much smaller cell, very small, where there is the possibility to do the same in the same time, low temperature and high pressure.
Yes, and that was also the last question was the same comment that you just made from one of my colleagues in our American office saying that Almax has this cell. I believe it's called the Tozer DAC for anyone who's interested.
Yes.
Yes, okay, and that is all of the questions, unless anybody wants to try and get one in quickly before we finish. If not, I will say thank you very much, Laura. That was a very nice introduction to high pressure and the 120 DAC as well. So thank you very much.
Thanks to you to invite me. Thank you, Fraser.
You're very welcome. So I would just like to one last time say that our next topic webinar will be on the 29th of May, the same time of the day. So if you would like to join that, please check on the Rigaku website for the link to register. Thank you again, Laura, and thank you all for attending, and we'll see you next time.
Thank you. Bye-bye.
Bye-bye.